Hello, everybody, and welcome to another JUXT cast. It's me, Malcolm Sparks.
Me, Jeremy Taylor.
Me, Joe Littlejohn.
And what's happened since we last met? I think we had a conference XT24. Joe, do you remember that? That was last month. What
Just
was it?
about. Yeah. So that was our dedicated fintech conference run by JUXT. I guess we have a JUXT conference every leap year, so they're extra special. It's not an annual event, but it was a great time. It was held in Milton Keynes, so we did have to drag people out of the city and out of London to Milton Keynes, but it was a fantastic day. Yeah, lots of talks from across the fintech spectrum: investment banking, hedge funds, those in fintech that are outside of the banking space. So yeah, not just JUXT customers there to say how great JUXT is, but lots of people from our network and businesses that we know. And I think everyone had a good time. What about
Yeah, it
you?
was great. Yeah, we did. Jeremy and I did a XTDB version 2 kind of launch, wasn't it? It was really a coming out party.
Yeah, I mean, unofficially, it was a sales pitch, I suppose, but no, it was a nice sort of roundup of the business proposition for why we're building XTDB, the relevance of the bitemporal data model in risk systems, and the way that different people and trading floors need to scroll through timelines to figure out answers to questions quickly.
Yeah.
But no, my favorite bit was just getting out onto the balcony at the end of the day when it was the sun was up and we had good food and drink. It was a good conference.
Yeah, it was lovely. And we had a great panel discussion in the afternoon, and we invited a few people. It was Vlad Yatchenko and Francine Bennett and Mark Burgess. And Mark lives in Oslo. So Mark flew over to the night before. And so we had a nice evening with Mark discussing all kinds of things. Mark is the kind of the originator of a very early DevOps tool, I'd call it, a CF engine. Mark joins us from Oslo. Hello, Mark.
Hello, guys. Nice to see you again.
Yeah, well, thanks very much for coming over to XT24. It'd be good to get, just for those listeners who don't know who you are. Do you want to give a quick introduction to yourself?
Okay, my name's Mark Burgess. I was professor of computer science. I'm trained as a theoretical physicist. I went into computer science. I was professor at Oslo for 15 odd years or so. You may know me from such movies as CF Engine for Home Improvements and The Revenge of Promise Theory. And these days, I kind of work as a consultant on all kinds of things, technology and business and leadership.
That's great. Do you want to give us just a quick introduction to sort of promise theory? I know that's kind of it's you've written books, and so I'm not asking you to condense the whole books into a few minutes, but just for people, just to get a general gist, because I think that's going to kind of
I
what
can
we're
talk really
after.
fast. It's
So,
okay.
yeah.
No, so promise theory actually sort of came about by accident when many years ago when I was working in configuration management, and I became sort of disillusioned with the theory going around in computer science at the time for configuration. And it's very much the story in computer science that we should impose our wishes onto the devices and command and control them. You know, thou shalt be this device and thou shalt have these configuration settings, and you'd better step up quick to it, and comply with the obligations that are being imposed upon you. And I realized that first of all, this kind of model is very old-fashioned, and it doesn't take into account the very obvious criterion of access control, which is very important in security, obviously. So if you simply don't have permissions to order these devices around, you're not going to get very far by jumping up and down and stamping your foot and trying to have a hissy fit over things or whatever. But what we should really be thinking about is models in which the devices will only comply by essentially voluntary cooperation. Right? If they are ready and willing, if they're listening and they are awake and they have the capability to do certain things, then we can make requests of them as long as they're within that sort of menu that they're offering, and try to manage systems in that way. So you can imagine, rushing into McDonald's and demanding steak and chips, but they're only promising to deliver, 4 Happy Meals or something, so you won't get very far. And at the same time, you're not the manager of McDonald's, so you can't just boss them around. They're likely to, give you an English greeting or something in response. So this idea of obligations as the model for command and control just seemed flawed to me. But everyone was using it, and no one was talking about anything else. And there's this 50-year history of something called deontic logic, which is the logic of commands, which I didn't know too much about, but I started to research it a bit. And I met a friend of mine, or actually became acquainted with a later friend, Jan Bergstra from Amsterdam University, who came to see me. And he is a professor of logic, and he knew all about this. And he told me that, in the 50 years of deontic logic research, basically nothing has come out of this. The logicians love it because they can write all sorts of fancy formulae, but basically nothing has come out of this study for 50 years. And I told him about this idea of promises. Well, what if, we think of the world as a bunch of agents that are essentially autonomous to begin with, free, independent, causally independent things. So you can't boss them around with unless they're willing to comply. They would be either unable or unwilling to comply. You're not going to get very far by bossing them. So what if we consider everybody to be an agent like this? And we simply ask them to promise what they're willing to do. And then we try to adapt to those promises that they are offering. And we say, okay, we're willing to select or not select those promises they're willing to do, just like McDonald's offers their menu. And we say, okay, I want that one, or I don't want any of them, and I go somewhere else. And at first, he thought, well, why didn't anyone think of this earlier? And surely there must be something wrong with this because, it sounds like nothing logicians have talked about ever. But then over the years, he kind of came around and realized that this is a very powerful idea. And now I would say he's a convert. And we ended up writing the book together about this. So, 10 years later. But yeah, it was 2004, and they came up with this idea and presented it to the conference in Barcelona, Network Management Conference. And it actually ended up winning Best Paper Award because this was something like a revolutionary idea at the time. But it seems like a very ordinary idea to me. And even though it's quite ordinary, it's somehow taken 20 years to understand the implications of this. As more and more people catch on to it, the idea has spread into areas from computer science to agile development, software development, cloud computing. Obviously, the Kubernetes story is somehow tied to promise theory. The CF Engine story, of course, is tied to promise theory as well. I used what I had discovered in promise theory to redesign the whole of CF Engine, from going from CF Engine 2 to CF Engine 3, which is the current kind of version out there. So yes, it's something that I stumbled into and yet has kind of taken over my life in a way.
Wow. Do you find, you mentioned it's applied in software architecture, and I have a question. Does it lend itself more to directly to systems that are agent based? So I'm thinking about the Erlang actor based kind of, or where you model each individual actor in the system, or is it really just a way of thinking? Can you apply this to in any computer language?
That is a great question that sort of really goes to the heart of the whole story, right? Like, what is an agent? What is a system that's not an agent? Surely it's like in chemistry, you have, we originally thought there were all these mystical substances, earth, air, fire and water, and gold and metals and so on. And then somebody came up with the bright idea that, well, maybe everything are made of atoms of different kinds. And we can reduce everything to these basic kinds of stuff, which are basically agents in chemistry. And then there is the chemistry of those agents is what happens when you put them together. Well, atoms become molecules, they become new things, new substances. You put a lot of them together, it becomes a solid or a liquid or a gas, and so on. And we've developed our whole story of the material world around this idea. In a similar way, you can imagine developing the story of systems around atoms, which are basically agents. To some extent, this agent model in promise theory is compatible with the notion of actors in the actor model of computing. But there are some subtle differences. And then the thing that people don't always get is this notion that promise theory is not a philosophy, right? Because everyone in computer science and agile and leadership, they all want a philosophy to tell them how to live and be, good people and whatnot. But it's really just a method of analysis, like a form of mathematics or a kind of physics, if you like, just how stuff works. And so you use promise theory without any notion in mind as this is the right way or the wrong way to build systems. You simply follow a method in which you break things down into atoms, where atoms are agents at some level. And then these things don't do very much on their own, so you need to put them back together to make something more significant. And then you ask the question, well, can I put the things I have together to make what I want? If so, how? And then how does that change and how does it scale? How do these processes that come out of these different things I stick together scale? And then how do these talk to potential users or whatever the situation is? So promise theory is kind of a neutral arbiter for talking about systems, breaking it down into its component parts, and then seeing how to put those things back together again and finding the possible flaws or missing promises, if you will.
Does promise theory imply then that, so one of the topics, the central topics, I guess, of XT24 was kind of the benefits of centrally orchestrated workflows over, a choreographed system or a more decentralized approach to achieving goals. I wondered if promise theory implies that or works best or is best applied in scenarios where you have a central orchestrator that can make those combinations based on the available, contracts, or do you use the term contracts in promise theory?
For me, a contract is a bilateral collection of promises. But yes, a contract is formed from promise. So promises are more elementary things than contracts. Contracts are kind of molecules, if you like, in that picture. I think that your question is a great one again. Centralization, decentralization. This, of course, is exactly where I objected to the notion of command and control and obligation-based management way back in the days of network management, because everybody and their dog, have thought that you had to start with centralized command and control to manage systems. You have a king sitting on his throne who says, "You'd better do this, you'd better do that, and I will govern and rule as a dictator should." But this clearly isn't how most systems actually work. You can try to command and control with, sit with your remote control for the TV and point it at things repeatedly to get your stuff done, but it doesn't always work for a variety of reasons. So I kind of started with this prejudice about systems that probably we should think of them, and probably systems would work more reliably and robustly if they were completely decoupled from one another. Because one thing we know in physics is that weakly coupled systems are often more resilient to shocks and problems and errors and faults. Metals stretch, rubber bounces back, and so on. Whereas you have something very rigid and brittle like glass that tends to shatter into lots of pieces. And many people use that analogy when they're looking at systems. If you have a tiny piece that breaks over here, the entire system goes down because it's so tightly connected. So these analogies for computer systems and human systems, for that matter, as rigid or loosely coupled command and control systems or cooperation systems, has been very popular. And the logic of obligations kind of tells you must have that central controller to manage everything, to keep a central, like a brain that rules over the system, to know everything about it. But distributed systems don't always work like that. The classic example, of course, and the highly successful system that we rely on every day is the routing system, the network. And there are literally no network protocols that work by command and control, or at least there weren't until Google tried to reinvent them for its data centers. But all of the familiar ones, the RIP, OSPF, BGP, all of these well-known things, they all work by loose coupling independent agents working together, publishing information that they have, allowing others to see it if they have permission, grant them permission, and you don't have to. This is sometimes the reason why BGP fails, because people don't have permission to see the routes in a certain direction. And so over the years, I thought, well, these robust systems are probably decentralized. But over the years, I also learned the hard way, almost by having that prejudice, that actually there are fundamental reasons why you need centralization sometimes. And promise theory kind of showed me the necessary and sufficient reasons for wanting centralization. And it's basically about calibration. The reason you want a single agent to talk to lots of different agents is to be a single point of reference, right? Because when you have a bunch of unruly distributed systems, they all have their own measures, their own standards, their own clocks, their own sensory devices. They're probably not quite in line with each other. They're not calibrated with one another. If you want to set them up and calibrate them, you need to compare them to a standard source. And that is the point of centralization. Just as, when we have meetings for people, if you want to send out a bunch of information, you don't need to call people into a meeting to do that. You can just post it out on Slack or whatever, or post it out on a wiki or something. But if you need everybody to raise their hand and say, I vote for that president or whatnot, you need them to all show up at the same place at the same, more or less the same time, within some limits, within some scope. And that is the meaning of centralization. There is a scope that's defined for a certain amount of time. And within that amount of time, this is where we get to compare things and decide whether or not they're the same by some common process. And so that is actually what comes out of promise theory as being the important aspect of centralization. And we use it and we abuse it. But I think that's also almost one of the success stories of promise theory, to understand the righteous role for centralization.
Yeah, it's interesting you mentioned the internet. That was exactly the thing I was thinking about when I used to get called in to dial up to investment banks to 2 o'clock in the morning because a certain computer system in the bank, like a risk system, had fallen over, and there would be, we were panicking, we couldn't get the risk in the next day, and so you'd be logging in at 2 a.m. trying to fight with this thing, and then sort of just musing as you were waiting for for tailing the logs on NFS or something, and just waiting for some feedback, thinking about that you've actually logged in to the system over the internet, over a system that's been running for 30 or 40 years. And
well, so there's another case of that, right? I mean, the banks do this every day with the clearing. Clearing is exactly one of those processes where you've got a whole bunch of distributed stuff. But in order to resolve the potential inconsistencies and disagreements from all these different processes not being kind of in alignment, you give it a grace period. You create a scope, a protected scope, in which these resolutions things will be resolved, and the final decisions will be made on whether this is this or this is that. Did the payment get made, or do we roll it back, and so on and so forth. And it's exactly the same reason why you have a kernel in a database, which is a protected environment for making database transactions. You want to isolate that region over a scope, a centralized scope of space over a certain amount of time to again decide whether one transaction won over another transaction, and we have to roll it back or reverse it or whatever. So it's that process of resolution, of accepting what has been offered as a promise and deciding which of those promises will be accepted and which will not be accepted, which is the function of that calibrative centralization.
Yeah, yes, indeed. I mean, we have in the last couple of years, and I think other listeners will know that we've been talking about a kind of conceptual architecture called atomic architecture, which is a sort of a kind of statement that if you do need to create consensus somewhere, that you need consistency, you're better off doing that in one place, so rather than many places. So it is this desire of us to distribute all the things, but to understand where you actually need centralization for those small points where you need everybody to come together. And the examples I use are people booking an NHS appointment in the UK. They don't want to. You don't want to book NHS appointment and turn up to the hospital to realize that there are two people who come for the same booking in the same room with the same doctor, or you buy something online and it's they take your payment but they find there's no stock in the warehouse, or those sort of problems where you have to then cancel the transaction and work around all the problems of inconsistency. And we're using words like transaction and consistency here because these things have this idea of the automated clearinghouse is that central, that atom. And indeed, the reason we call it atomic architecture is that it's loosely modeled off this idea in the closure language that we use, that mostly everything is distributed, pure functions, and everything just works with immutable data. But occasionally, you need some, you need to have something in the system that is coordinated and that says this is the state of something. It's going to change, and that so changes are atomic and these things are called atoms. And so
Right.
there is a sort of another reference type enclosure called a promise, but it has a slightly different kind of semantic. But it's this idea that occasionally you want as much distribution and parallelism as you can get away with, but as soon as you need some agreement, like coming in to vote on something, or that's when you all arrive. We all go into the same place to have a vote. And
This concept of closure, of course, in computer science, from which the name comes, is essentially exactly that notion of the bounded scope over which you are trying to assure some consistency. And actually, you remind me of a related problem here. You talk about the NHS. Another problem, which I know doctors have in many countries, Norway included, is that doctors, of course, are restricted in the kind of information they're allowed to share with one another because of patient confidentiality. But they all need to share certain things like parts of medical records, maybe an X-ray. Radiology has to share it with the GP and so on, but maybe not the whole thing. And so there's a need to share little fragments of information that come from many distributed sources with one another on a certain basis and make that information consistent. And this brought actually me and my colleague Andras Gerlitz in Hungary, has been making a system precisely to coordinate these silos of information where data can change, data which are potentially shared information, but they can change in any kind of location, and those updates need to be shared around a certain group of specialized, privileged individuals. So, for example, in a security scenario, you have a similar story where, let's say, you have access to a bunch of systems, maybe it's a bank or whatever it is, and for whatever reason you lose your job one day and they cancel your password, your credentials. You want that repudiation of your access rights to be instantaneously reflected in all of these independent systems. And so that consistency of data has to go the other way as well. you make a decision centrally, and then it has to happen at exactly the same moment in all of these systems, whatever at exactly the same moment means. And you have to define that because it's fundamentally ambiguous. And so you have this story about data coming in both directions, from the edge to the center, or from the center to the edge, and the consistency needed between them. And then understanding those necessary and sufficient processes for that has been an extremely long-winded and difficult process in computer science. We had Paxos in the beginning, and then we had the Raft protocol, which are designed to use a very strange idea of voting on what is the right version of something. It's like, we maybe vote for who we want for president or prime minister or something, or maybe we don't even want to do that, but voting on which is the correct version of my X-ray, well, not sure I want to do that, actually. I would like to know which is the actual one that came from the proper authorized source. And so we've muddled this notion of authorized bona fide correctness with the idea of, well, if we all put our hands up and decide how many of you have got the same one, okay, well, we'll use that one then, which is obviously actually vulnerable to all kinds of different attacks. It's a very strange idea, but we can solve that problem if only we wanted to. And promise theory kind of shows you how to do that.
So I guess for most of us who've worked on, large computer systems, I think one insight that you pick up is that if you're working with a sufficiently, complex or large system, you get to a point where all systems are in a constant state of failure. You try to minimize it, you might try to isolate it, but there's a level of scale and complexity where you have to accommodate failure and decide how you're going to handle it, and it will be likely be the case that there will be failure somewhere in the system once you've reached that sort of a tipping point of scale and complexity. So I'm interested to know how in promise theory, how do you deal with broken promises, and what does promise theory have to say about broken promises and strategies for dealing with them, or what the implications of them should be?
Exactly. And this, of course, is the big difference between the logic of obligations, where you're basically not allowed to not keep your promise, or not allowed to not keep your obligation, and promises, which is a best effort kind of model. So the idea of failure is built into promise theory. If the promise is broken or not kept, as we say, it's basically hard luck, because an agent can be unable or unwilling to comply for a whole variety of reasons, which the centralized entity, whoever it may be, knows nothing about. It doesn't have access to that sphere or that scope necessarily. And it may not be anybody's fault, so it's not a question of blame, but it's about how do you build systems that are robust to those failures anyway, in spite of that not being able to keep a promise. Interestingly, one of the things I did with promise theory was to say, I got involved with IoT, Internet of Things, and edge computing 10 years ago when I left the CF Engine company. And a lot of the story there is about independence and being, connected or not badly connected to the central data centers. I remember when my Google Home, when you lose the internet, Google Home switches on all the devices in the house in the middle of the night. If the internet goes down, suddenly it'll turn on all the lights because it's lost its brain. Oh my God, what am I going to do? Of course, I'm going to wake up all the humans, which is kind of a nonsense thing to do. But this is the fallacy of trying to rely on centralized control by brute force, which all the major companies in the US tried to do, from Google to Cisco to the whole bunch of them. But I asked this question: what would happen if you tried to understand the whole world we live in as a kind of smart space-time, which every volume of space is like an agent, which makes some kind of promises, right? This bunch of air in front of me is is an agent which promises me oxygen and, the ability to breathe in a certain temperature to live in. My printer at the side of me promises to print when it can be bothered to, as long as it has a bunch of cartridges which are not empty and so on. So there are dependencies inside it as well, which may be concealed by the outer shell. So it seems to be a flawless device printing stuff, but actually it's pretty unreliable because it depends on some things which I haven't thought about. And so if I try to oblige it to print for me, it may be unable or unwilling. As we all know about printers, all of us have tried to use printers.
That's when you get the baseball bat out.
Exactly, the baseball bat obligation. And this is a way of modeling the world around us, right? So a book has promises to teach us something about computing, or tell us a novel, tell us a story. And I know we want to come onto the problem of energy and so on in the coming discussion. So you imagine a bunch of solar panels, promising to deliver a certain voltage electricity as long as it's not too cloudy and as long as it's not nighttime. So the promises that things are actually able and willing to produce are, first of all, subject to a whole bunch of dependencies which make them potentially unpredictable if we don't know about them. And a lot of systems don't expose those dependencies to their users in a clear way. So, for example, my bank, I hate it. It pretends to be this, 24/7 thing that never goes down and gives me all kinds of services. And I can bet my life that, a large fraction of the time it doesn't work. Can't even log in. And, let's not go into that too much right now. But we can model the entire world in this way. Now, one of the things that occurred to me, because I'm a physicist, is if you treat the world as a bunch of atoms that are communicating and cooperating in this way, suppose we try to make that compatible with information theory. Claude Shannon and his story about the transmission of signals. What does it mean to transmit information from one thing to another? And let's suppose everything's made up of a computer. It's about as fast as each other. They've all got the same, Intel chip or AMD chip or whatever. So they all have the same frequency of operation. They're sending stuff and they're listening. Well, Claude Shannon has the Nyquist-Shannon theorem that says if you're sampling at a certain rate, you'll probably miss 50% of the signals if you're not quite in phase with them. If you're not listening at quite the right amount of time, you will miss that signal unless you're actually sampling at twice that rate. But that means that everybody has to be sampling twice as fast as everybody else, which doesn't work. So actually, in the real world, we expect signals to only be reliably transmitted at half the rate at which things would like to send them. So we need to be very careful about looking for error correction and listening. Did I catch that thing just in time? It's like the security camera, like in a building, it's panning backwards and forwards looking for thieves breaking in. It's panning at a certain frequency. And if you can run across the room fast enough so that it's, it misses you and it's turned in the opposite direction, you'll get past the camera, it won't pick you up. And it's exactly the same with all our communications devices. And any model of computing systems will have this ability for promises not to be transmitted faithfully from one agent to another. And we have to live with this non-determinism. It's actually, I believe, probably the reason why we have non-deterministic systems on a low level in physics, quantum mechanics, because precisely the universe is made of these elementary systems that all sort of vibrate at a similar frequency. And so half the time they're going to miss stuff that's going from one to the other, and they need to be in phase. So unless they're actually phase locked by some larger process to transmit faithfully, there will be all this kind of noise and indeterminism going on. Same thing with computer systems. And this is what we need to build in to make systems robust. Also in human systems, of course, that's another story. So yeah, the timing and the way we break systems down are a major thing that we haven't understood very well in the scaling of computer systems.
So we've talked about quite a lot of abstract ideas, I guess, Mark. I wondered if you could just explain, for those that may not be familiar with it, what exactly is CF Engine, and in a kind of concrete way, how does it embody some of the ideas from promise theory in specific some technical specifics, I guess.
Okay. So at line 33 of the C code, there's an if statement. All right, no, seriously, folks. So CF Engine was a kind of a software robot that I wanted to build during the 90s when I was at the university working. We'd bought a bunch of Sun workstations. Nobody knew how to manage them at the time. Unix was still quite new. And of course, there were many, many different kinds of Unix, and it was spreading different versions of it all over the university. And in the beginning, it was kind of fun to learn how to configure Unix by, these command line jutsu moves to combine bash commands to get, well, it wasn't bash then, it was Bourne shell or C shell. And there's a lot of configuration involved in setting up a Unix system, right? It's a multitasking system. It has a ton of different processes to make the thing work. You don't just log on and run a program. You've got the kernel managing devices, the network, hard disks. You've got multiple users logging in, sharing stuff. You've got the screen, writing on the screen. You've got the windowing system, all of this different stuff going on. It all needs to be configured. You've got the email process, delivering and receiving email. Eventually, you had things like the web. Came later, of course.
So most people at JUXT use Arch Linux, so we know all about how difficult it is to get a system fully configured.
But so the first idea that everyone had was, of course, to make it simple, you just want to make all the machines the same. You want to make an executive decision. You push out a bunch of images to machines to make them all the same. Just try that at a university, and you'll pretty quickly get the sharp end of some professor's tongue, I tell you.
We had the same at
everyone at
JUXT.
the university.
Vim versus Emacs, by the way. So, you just
Yeah,
try and push
exactly.
everybody.
Right, so everybody is a special kid at the university. They all want their own things, and they all demand their own little fiefdoms about this. I want this program, not that program. I don't ever want that thing on my computer. I want my backup to be done at 11:30 and 56 seconds, or else, all of these wishes that people had. And so the goal, I realized that one size fits all wasn't going to cut it. So I couldn't do it by hand, obviously. And it certainly wouldn't, even in the physics department, I couldn't do it, but it wouldn't scale to the rest of the university either. So I figured we needed a robot or an automatic system to do it. So I was interested in sort of artificial life and things, Gödel, Escher, Bach, and all of those classic books in AI. And I thought, well, maybe I could write something because I'd always enjoyed writing systems. So I started making a language where you could separate just what you wanted to be the outcome from the method you would use to make it happen. And you would kind of imagine the machine figuring out how to make it work. But let's set that aside and just create a language to express intent so that everybody could express their own intent and say, I would like to promise that my machine will take that backup at 11:30 and 56 seconds. And I would like the send mail program to be configured in this way, sending to that mail exchanger, whereas somebody else wants to use a different mail exchanger, and somebody else wants to use the other damn thing that I forgot the name of, not post send mail, but post whatnot. And yeah, there are many of them now, of course. But there were all kinds of technical challenges to solve, weird text formats used by, it's literally like a bunch of Egyptian hieroglyphics to configure SendMail or an encrypted string in RSA. So there's all this sort of very finicky, detailed stuff to be done, which lends itself to machine work, manipulation. And there are all of these independent desires and wishes that need to be compiled and formulated and responded to in some kind of real time. So I designed an agent which would read these things and kind of observe the state of the system like a robot and say, okay, I'm waking up. The time is 12 p.m. I see that this is a SunOS 4.13 system. It's it's got these patches and it's got this software installed. And I figure out I'm in the physics department because I see these IP addresses connected to me. What am I supposed to promise to do? Okay, here's my policy, and it's 12 a.m., so I need to do this, this, and this. And these are my promises. Okay, now I'm going to try and keep them. And this agent would work, as hard as it could to try to keep these promises and converge the system from whatever weird state it might be in to the desired state that it was trying to promise that it should be in. Because, of course, no matter how hard you try to exclude humans from the loop, there are all kinds of people logging in, making changes they weren't supposed to. And so sometimes you would get people fighting the automation, right? They would want to change this thing, and then the automation would want to remove that thing or change it back until they learned that there was some sort of proper procedure or protocol for going about making changes. But so CF Engine was designed to be this automated, somewhat smart system that adapted to its environment and context by sensing its environment and figuring out what it needed to do to converge towards a desired target state. And I wrote this first version in 1993 and developed it over the next, until today, essentially. I left 10 years ago, but it's still around today. And it is, even towards the end of the 90s, it was doing some kind of machine learning to figure out when is the optimum time to do a backup and all of these complicated things that I could think of. Then later on, the concept of configuration management was kind of dialed back to something much more simplistic. I want these configuration settings to be this, and I want these packages to be installed, as things became much more commoditized. But my original idea was much more AI robotics inspired. But you would use this to basically manage systems and get the system to do all of these complex things and even orchestrate processes, even though every single system had to be formally independent of the other. There was no way we could oblige systems by command to obey these commands from a central point because the professors wouldn't have it. So every computer, so CF Engine was designed by design, it was impossible to send it instructions. Right? It could only choose voluntarily to pick up instructions from an authorized location if it wanted to and when it wanted to do updates. So it was entirely based on voluntary exchange of information and cooperation. Later on, these things also got dialed back much more to the command and control thing when we got into cloud, because in the cloud, of course, everything was SSH based. It was all push out. I want to dial up a machine, and then I want to dial up a configuration, dial up some containers. So we went much more back to that individual push-based thinking. But now I see people going back again. And of course, when Kubernetes came out, they realized that that wasn't going to fly in a lot of cases for things they needed to be able to keep promises on a voluntary basis and respond to failures. So you would imagine the system being unable to comply. You maybe need to reset it or start a new one or get some more help from some other devices that are going to be dependencies and so on and so on. Long story short, this was a model for cooperation which has fallen in and out of favor over the years, but is always, in my mind, very important for managing the resilience and reliability of what we want systems to be able to offer as a service, as a promise, in order for users to be able to consume those services in a reliable way, and possibly, have some kind of predictability around it.
So I think One thing that's really interesting, and I think this is actually a very, very powerful kind of system design consideration, is that it's this concept of convergence. And in a way, it's, again, if you're working with a small piece of mutable state, and it might be, as Malcolm says, the contents of an atom in closure, or it might be a single database, let's say a sort of small database. You may be in the situation where your application can control all changes to that state, and you can have quite some confidence in what possible states do we have in the system. When you're working with a very large system of very large mutable system, let's say, all of the software configuration that makes up one of your machines, or in Kubernetes, the Kubernetes is a vast mutable thing. So I think in that scenario, the notion of convergence, which is effectively saying, there may be many different ways in which this system changes, and there may be changes that are desirable, changes that are not desirable. But what we need to focus on is the target state, rather than all the possible transitions that we might have to roll out. What we want to do is not necessarily assume the state of the system, but we want to be able to check and decide, I don't actually care if how one of these things got into a state that I wasn't expecting. But what I do want to do is always be able to converge on the target. And it's interesting that, in a way, those those methods of managing infrastructure own things like Ansible or other systems that were sort of trying to continually use that approach to maintain something that was mutable, started to become less popular as the notion of immutable infrastructure arrived. And as you say, what we do now, create a Docker image, and we actually know that can't change. We do know that to some extent what the limits of incorrect state might be now in this system, and we only change it in a certain way by creating a new image and rolling that out. And I guess in the case of Kubernetes, we don't have that notion of an entirely immutable system at the cluster level.
Yeah.
And so with this notion of convergence is still very, very powerful there. And I think that this notion can actually be applied in lots of different systems. It's a very powerful, system design method, is to think about, are we in this situation, and should we think about converging on a target rather than trying to predict and codify every possible state change.
I mean, I'd like to add to that, because I feel that the idea of convergence has almost been sort of forgotten. And I'll give you an example. I mean, one example is um, the issue when you kind of make one change to a piece of documentation and then you have to rebuild the entire website again, or I've been building Amy's in Amazon, and we have this rock project in JUXT where that it uses Terraform Packer to HashiCorp to Packer and if I make one mistake, and then the whole thing has to be built from scratch. We SSH onto a machine, it downloads a base AMI, it carries on building and building, and then that's 20 minutes later, and then, oh gosh, I forgot to install a package. Right, let's do it again, 20 minutes again. And there's something in that 20 minutes, or waiting for that 20-minute build to happen because you made one small change where you think, surely, I mean, why do we, and there is definitely this I think a fashion that came from, well, it came around agile days. I think early
Yeah.
ThoughtWorks, cruise control, configuration,
No.
CI/CD pipelines, where everybody's kind of the only mode of making any changes to make this go right through the sausage factory again and make a
Yes.
new packet of biscuits. And I've always questioned whether this is the best thing that we should be doing, just from a pure efficiency point of view, from a time-based point of view, from an ecology point of view, and a waste point of view. Why are we so obsessed about building
I
everything from scratch?
could not agree with
That's a
you
big
more.
question. What kind of biscuits are you buying, Malcolm, that come out of a sausage factory?
Well, I eat a lot of biscuits, just for the record, but not notwithstanding. This was actually an argument that was raging at the beginning of the CF Engine days when I set up a workshop, at least 2000-ish or 2001, I think it was, when I was chair of that conference, and we called it the there was a camp for Convergence, which was the CF engine approach, versus a camp for Congruence, which was the build it from scratch and follow the same recipe every time. So you make it congruently from the same initial state. And the difference between it is, right, is do you have a predictable initial state or a predictable final state? Which boundary condition do you want to fix? For me, it was a question of continuity, because remember back in the 90s, we only had a few machines, a few hundreds of machines, maybe at the most. It was a big deal if a machine went down. You didn't want a machine ever to be out of service, and we'd be trying to keep them up for hundreds of days at a time. So you wanted the system to be up and running and converge towards that state while it was still in operation. And there might be a little window in which it wasn't perfect, but at least it was mostly doing its job. It was a shared resource. With the Congruence approach, of course, like you say, you hit Control-Alt-Delete, or you blow up the power station and it all collapses and you rebuild the thing from brick by brick, which is obviously wasteful and energy inefficient and time wasting. And there's this window of failure in which it's unavailable. So exactly as you say, the thing that changed, of course, is the cloud gave us new methods of ensuring redundancy. And we make these more service-oriented systems that can fail over to redundant servers. So there are ways around it for the continuity argument, but it's still energy inefficient. And if you think about the amount of energy that goes to waste in the cloud every day, rebuilding senseless software, it's enormously wasteful in terms of CPU and communication.
Yeah, but the one, at least it's only a tiny fraction of the amount of energy that's about to expended on AI, large language model transformers. So
Absolutely.
there's a drop in the ocean.
Speaking of energy, I read one of your blog posts, Mark, which was very insightful about sort of alignment or agreement to mistrust. And you made an argument in there about how energy is essentially conserved by people agreeing to not trust each other at certain points, right? So because to verify things takes energy. I just wondered if you could talk about promise theory from that angle, because I thought that was quite an insightful thing.
Oh, this is a really interesting thing. We don't. This is a whole different podcast by itself. But I had this sort of I've always been interested in social systems, and even as a physicist, I wanted to understand. Can we do the foundation trilogy thing about predicting the future as a a model? And I had this crazy idea that trust would somehow maybe works in the similar way to the way energy works in physics, as it's an enabling thing, and it's the flow of energy or the flow of trust that makes promises be kept and enables processes and services to be continuous, that continuity we were just talking about. And I've done actually a lot of work on this now, and it really does work out extremely well as an argument that there is this analogy between energy and trust, to the point where there's a kind of potential energy or trustworthiness, an assessment of how reliable we think people are, which is a kind of a landscape of trustworthiness that we use to make decisions about. And then there's a kind of kinetic trust, which is how often we how often we check, or how well something is going, how often we interact with something. Are we there yet? Are we there yet?
So to play that back, I mean, the trust that you would have in an individual would be the trust for that individual to keep their promises,
Right.
And then and the verification of that trust is how do you trust the trust?
Yes. Exactly right. So there are these two forms of trust rather than just one, which we've kind of assumed. And they behave in very different ways. And like you say, there's this close relationship to promises. It's kind of feedback thing between like energy and motion and so on. You don't go and ask for a service or a promise if you really don't find an agent to be sufficiently trustworthy. And that trustworthiness assessment comes from all kinds of feedback processes in the environment about how well it's likely to keep its promises based on past experience. And then once we've sort of gone and dipped our toe in the water and gone for it, we still kind of have some residual mistrust, which guides us to how often we want to check and monitor the system to see if it's working as we intended. If not, we want to tweak it or change our relationship somehow, and so on. And this gives a very good model about how systems can work, particularly distributed systems. Again, if we go back to this example of distributed energy, everyone with their solar panels wanting to sell the residual surplus energy to the grid back and forth. You can imagine people claiming they're going to send a whole bunch of energy at a certain amount of time. Yes, I've got this number of panels. They'll all be available at this time. And then they go and they turn on the bubble bath or whatever, jacuzzi, and then suddenly it's unavailable. So they lied somehow, or they didn't keep their promise. Similarly, you want to realize that the receiver might be unavailable to receive that energy when the time comes for all kinds of other reasons, because it's busy doing something else. And in the olden days, of course, the grid was managed just by these fluctuating analog potentials, which at a certain point might blow up a substation because it's like a lightning strike comes down, or we have a solar storm, as we had recently, pumping energy into the grid, and suddenly it can't handle that voltage, which it promised to be able to handle. It couldn't receive it. That becomes a problem for managing the grid. It could even be a greater problem once we digitize these systems in the future, because the stability of digital promises turns out to be much more, what's the word? I've forgotten the English word for this now, sorry. Sensitive. There we go. Sensitive. It's much more sensitive to broken promises and the degree of promises than an analog system. So again, you go into McDonald's, you've got 4 Happy Meals. You can have one or the other, but to some extent, you can change the number of onions you want on your burger or something by some additional tweaks, plus or minus. But you can't say, give me 36 grams of onions or something. Whereas in the electricity grid, the degree of variability in the environment, a natural environment, which is fluctuating on all kinds of levels, it's way beyond anything digital. So you can imagine a much more chaotic system trying to be managed digitally than even the analog system. The analog system either works or it doesn't until it blows up. But the digital system may make fundamental decision errors and predictability errors based on machine learning, digital levels, controllers, etc., because the promises are too coarse in their variability.
Yeah, I'm getting a just. I mean, I do have a sense. I think most people have a sense that digital systems are more fragile, to use and sensitive than analog systems. Analog systems have a sort of equilibrium that kind of gets established. They tend to track towards something that's stable. I think most people experience it that that digital stuff like your modern TV just doesn't work. Analog TVs tended to work all the time until the tube went, or something had to be quite wrong. You might get some static, and it might have to tune it a little bit, but don't go wrong in terms of a TV deciding to turn itself off, or having to wait for an update, or not losing an internet connection, or just needing just generally not working very well. And so there doesn't seem to be that natural equilibrium that digital systems arrive at somehow. And perhaps it's because they're too coarse grained, and so they don't have that kind of natural balancing capabilities.
I actually wrote a book called In Search of Certainty 10-ish years ago now, which is exactly about that. Basically, how do we understand, excuse me, how do we understand equilibrium and resilience and reliability of systems? And then how can we adapt that to a promise world, and then to a digital promise world, and understand how to command and control or orchestrate or choreograph, or however we want to express it, systems in the modern world to satisfy our needs and desires.
I think it's one reason why Apple was famous at one time for skeuomorphic design, and kind of equating within software systems some kind of notion of kind of the physical, whether it's analog buttons and switches, because people were so comforted by having that sense of interacting with something analog, and that they feel like they're turning a nice a nice dial or flicking a switch, because it gave that comfort that this will work and it will be predictable and it will do what there's not 100 ways to that this system might fail, or that you might just not quite hit that button or not quite pull that switch.
Yeah.
Because there's something so I guess everyone really does have that sense of trust in those analog systems that doesn't come from nowhere. It comes from, as you say, because that predictability and that certainty over how they work.
I mean, I would like just to offer by touching upon something, and as a solution to, or as a theory as to why analog systems are more robust, and I think it has to do with it's something that we touched upon before, which is error correction. So natural systems that we perceive are naturally error corrected. I mean, an error correction is everywhere. So it's seen in the natural selection. So a plant might wilt in the sun in a hot temperature, and so it's as the sun the plant's future generations might be slightly better adapted or worse adapted, and the environment is selecting the better adaptation. So there is we were talking about agile being a kind of error correcting mechanism. You start building with a process, and then you might make slight changes to that process. You measure them with feedback and say, all right, or refactoring is the refactoring is an error correction mechanism. There's a nice there's a Oxford professor called David Deutsch that he's done. We've had a few discussions in JUXT about some of his theories, but he has a sort of theory, kind of a thinks that this is a universal theory, and even to the point of we're in the UK, so we have an election next week. That the election is an error correcting mechanism. In David Deutsch's kind of explanation that the government could be the error and the election is the correcting mechanism, and democracy is really the ability for you to get rid of bad leaders and bad policies, and that's kind of his definition of democracy. So I point this out because there's a sort of vast number of examples here of where error correcting mechanisms have evolved or exist. But in digital systems, this is why I was going to ask about promise theory. You may construct a whole load of promises and contracts and intentions in a system, but the moment you get it wrong, only either because you designed it not quite right or the environment has changed and you start seeing lots of broken promises, it does feel to me we need to, if digital systems were ever to get as robust as analog systems, there would have to be something that we create in the digital world, which is like an error correcting mechanism where systems evolve. In a way, the internet is a kind of has that error correcting mechanism inside it, but it does feel like that is the time dimension of what we're talking about.
Again, what you say is exactly kind of nail on the head stuff. Back in this is the reason why logic didn't capture promises very well, because it's deciding a state that it wants you to achieve, and it doesn't say anything about how that state can be managed or how it can come about. What people misunderstood even about promise theory in the beginning was that it was about the desire, the intention as a reliable, achievable goal. What it's really about is the conditions under which processes can make things happen. It's a theory of process, not a theory of absolutes. And every process is liable to succeed or fail. It requires multiple attempts to make it happen, certain protocols necessary to transmit information, and so on. This whole issue of the sampling rate, the Nyquist-Shannon sampling thing. And this, of course, is why analog systems are more robust, because it's all about population dynamics. Analog systems are much more fine-grained. They're about large populations of waves of things moving around, herds of animals being selected in evolution. waves of electrons going through wires, not just one digital yes or no signal. So it's that sharpness of that clarity of intent which gets muddled with the robustness of the process. The fact that it's sharp and clear to us semantically doesn't mean that it can be achieved dynamically in the same way. And again, I wrote about this in my book, In Search of Certainty. I make the point that dynamics always comes first. You always have to figure out what dynamics do you have to play with. And you can try to build semantics on top of that, but you can't do it the other way around. You can't assume that I can have whatever I want and the meaning of it must be clear, and that I can always engineer a process to realize that. It's just not necessarily true. So we always have to live with what we can make.
As we wrap up, anything else to add? What's the future for you, Mark? What are you currently working on, or what sort of things what itches are you scratching at the moment?
I always have a lot of projects on the go. I mentioned the data platform project with Andras Gerlitz, which is the data reliability platform for all those edge-based systems.
We do have a podcast with Andras. It's just been released, I think. So
Yeah,
that's been
this week on
this
the
week.
Omni-Ledger system.
So that's probably the one of the previous episodes. Look out for that if you're listening to this.
I have another project which is about knowledge management. I've been very interested in knowledge management for the last 20 years. You know, how do you, first of all, represent knowledge reliably in computer systems? Given that knowledge is, again, one of those things that is a process, not really a set of absolutes. But we tend to record it and capture it in terms of little absolute samples to be regurgitated from books or databases. And because it's a process, we need to design data for processes to handle and not for searches to sort of regurgitate abstract bits and bytes about. So that's a very complicated story, but again, something I've worked on for many years. And I'm still looking at ways to realize that with modern systems. The technology has changed too fast for us to find a reliable implementation of it over the years, but we're getting to the point where it could be done. And then I've been working on some very theoretical things in between projects called motion of the third kind, which is a promise theory idea, which sort of describes motion in its most general sense and change as a promise theoretic construct, which allows you to connect the dots between quantum computing and classical computing in a meaningful way and show that our systems at scale have many of the features of quantum systems, which we need to understand, especially as systems get bigger and bigger. And we merge all of these uncertainties and non-determinisms into our systems. So lots of balls on the go. And I hope maybe to come over and work with you guys one day again. That would be a lot of fun.
Definitely. And if any listeners want to get in touch with you, Mark, for, perhaps to get your help in anything promise theory related and beyond, how do they get in hold of you?
I would go to my website. The easiest one to remember is markburgess.org, no spaces. And also I have my company, chiteki.org. That's harder to spell, so if you go to the first one, you'll find the second one.
Or we'll put both in the show notes, won't we, Jeremy? And we'll of course, do reach out to us if we're it's very exciting, and it was a lovely conversation that we had in the evening. We obviously had more time over dinner, and we had we definitely would. I'd love to touch more upon knowledge representation, because I think that is a hot topic at the moment. People are really struggling about how to turn data into knowledge, and particularly it's kind of a touch point today with AI and all of the hype and surrounding that. So no, lovely to talk to you, Mark. Really great conversation, and thank you very much for being with us. Have a good weekend, everybody.
Thank you so much.
Bye. Thank you.
Cheers.
Thanks.